Hello, I welcome you all in the course Mechanical Measurement Systems. Today we will discuss the strain gauges. The topics to be covered is only strain gauges today. Say for displacement measurements, we have discussed about the potentiometer, where there is a wire and effective length of the wire is changed in order to measure the displacement or any phenomena which is converted into the displacement. But in this process, the physical property or physical properties of wire are not changed. Physical properties means in the entire process, the resistance per meter length of the wire is not changed, or any other physical property. For example, length of the wire is not changed, it is fixed. Effective length change or cross-section area of the wire is not changed. Now, there is another device which is used for measuring the displacement and many other physical phenomena. But the working principle is the strain developed in a wire. Now, this strain developed is directly related with the resistance of the wire. For example, a thin wire of a length, let us say a particular length L, if it is subjected to some force, the wire will get elongated. It is a metallic wire, it will get elongated and it will develop a strain, and at the same time it will develop stress also. Under this strain, the length of the wire will change because strain is being developed. Strain is delta L upon L. So, length of the wire will be changed. Since the length of the wire is increased, volume is constant, cross-section area will reduce. It will reduce. So, if we take resistance of the wire is rho L by A, L is the length of the wire, A is the cross-section area, then the resistance will change to R dash with rho L1 plus epsilon, something like this, divided by change in the area, right? And this R dash can always be related with the change in the length of the wire, right? So, in strain gauge, this is the basic working principle. This is the working principle of strain gauges, that when strain gauge is put under stress, right, strains are developed, and due to this strain, the resistance of the strain gauge changes, and we meter the change in the resistance of the strain gauges and corresponding change in the dimension or the length of the strain gauge is measured. For example, there is a bar of 1 meter length. I fix a strain gauge here. Strain developed in the strain gauge will be equal to the strain developed in the bar. So, once I am able to calculate the strain developed in the strain gauge on any substrate, for example, this duster, suppose here if I put a strain gauge and I put this under tension or compression, in that case, level of strain is going, because strain is a dimensionless unit. So, strain in the strain gauge is equal to the strain in the duster. Now, once I calculate the strain in the duster, I can calculate the change in the length in the duster. And definitely when strain is developed in the wire, the resistance will change, and we will be taking the signals from the change in the resistance. Now, there are two types of strain gauges, bonded type and unbonded type. So, we will start with the unbonded type of strain gauge, unbonded type. In unbonded type of a strain gauge, there is a fixed frame and there is a moving frame. There are two frames. One frame is fixed, another is moving, and on this moving frame, strain gauges are fixed, or these wires, they connect moving frame with the fixed frame. There are 4 wires, and these wires are pre-stressed wires. all the wires are pre-stressed wires. Suppose force F is exerted in this direction and displacement takes place. Okay, so this is a moving part, this is a moving frame. This moving frame will move in this direction, in downwards direction. So stress in these two wires will be released because they are pre-stressed, like spokes of a cycle tire or cycle wheel, like spokes of a cycle wheel. So these are pre-stressed. So when this is push in this direction, so there is going to be relative motion between fixed frame and the moving frame. So stress in these wires will be relieved. So strain, they will develop some strain after relieving the stress, and these wires will be stretched. In fact, resistance of all wires will change. So this is just to magnify the effect, magnify the signal. This arrangement is done just to magnify the signal, and these four wires will make four arms of a Wheatstone bridge, right? 1, 2, 3, 4, and when the bridge gets unbalanced, we can easily find the change in the resistance and subsequently the displacement in this direction. So this they seems to be very they are very efficient. First of all, they are very efficient, and they appears to be very fragile. I mean, it appears that it is difficult to use them, but these strain gauges are very efficient. As a secondary transducers, they are often used as a secondary transducers in the systems. Now nowadays, bonded type of strain gauge are being used. Widely they are being used. Bonded type of strain gauge, it consists of a bonded type of strain gauge. Now, bonded type of strain gauges means that it is clear from the name itself. The strain gauge is bonded on the substrate. So there is a firm contact between the substrate and the strain gauge. And strain gauge wire is very thin. It is a metallic wire, and metallic wire is pasted on the surface, substrate. The size of the strain gauge may be of say 2 mm or 3 mm, and the wire is very thin. The wire thickness is approximately, let us say, 25 microns. Now, this is not the wire, this is the thickness of substrate. The wire may be of 5 microns. Very thin wire, and there is a grid of wire. Not a grid of, they are serially connected grid of wire. It means the wires are like this. Very thin wire laid on the substrate like this. Okay? So they offer very high resistance, and here suppose they are terminated. So they offer, and this is the effective length of the strain gauge. So they offer very high order of resistance to the current. So there is a parameter in strain gauges, that is gauge factor. Gauge factor of bonded type of gauges is quite high, and gauge factor can be defined as the change in the resistance of the wire for per unit strain. This is known as the gauge factor of the wire. Now in bonded strain gauges, because these strain gauges are prepared by just first of all etching the surface substrate, right? After etching the substrate masking of the substrate is done, because substrate thickness is approximately 25 micrometer, and then after etching, vapor deposition is done on the surface, and the vapor deposition that results in the thickness of the wire as 5 micron. right? So that is why for these type of bonded type of strain gauges, the G is high, right? And we can derive this value of G also as we know that resistance of any wire R is equal to specific resistance multiplied by the length of the wire and divided by area, right? Now, if you want to have dr, because as I said earlier, gauge factor is dr by r divided by dl by l, right? So, change in fraction change in resistance, ratio of fraction change in resistance and fraction change in length or strain in the substance. So, dr is going to be equal to a square a rho dl, let us take this as capital L, plus ld rho plus rho L dA, right? This is simple. Y is equal to A by B, then dy is equal to A dB plus B dA divided by B square. This is minus, okay, this is minus, right? So, now dr we can take from here. Now, there are certain unknown terms here, right? So, for that we will start with the V is equal to A into L. This is the volume of the wire. Volume of the wire is cross section area of the wire multiplied by the length of the wire. Now, dV is equal to ADL plus LDA. dV is the change in volume. So, change in volume is going to be ADL plus LDA and is equal to L 1 plus epsilon. This is change in volume. This is strain, right? Multiplied by A 1 minus, this is the final volume minus original volume. Original volume is AL. Volume is final length. Final length is length plus change in length, because epsilon and L will give the change in length. Area 1 minus nu epsilon whole square, because this is nu is Poisson ratio, right? So, this is pi by 4 d square, that is why it is going to be square of that. Now, what we can do, we can take dV as AL, right? We will take AL common, 1 plus epsilon multiplied by 1 minus 2 nu epsilon minus 1. Sorry, this will not be here. 1 plus x to power n 1 plus nx, because higher order term we are neglecting, because their contribution in the final expression is insignificant. Now, we can take product of this AL 1 plus epsilon minus 2 nu epsilon plus, minus 2 nu epsilon square minus 1. Now, here also this term, because epsilon itself is very less, much below than, I mean it is 0.0 something. So, a square of it, again this can be taken as 0. This will be cancelled out and we will be getting AL epsilon 1 minus 2 nu. Nu is Poisson ratio. So, now AL epsilon 1 minus 2 nu is change in the volume. dV. So change in the volume is AL epsilon 1 minus 2 nu is equal to ADL plus LDA. It is always there. Now, once we have this expression, ADL and LDA, and L epsilon is B equal to DL, because DL by L is equal to epsilon. So L epsilon is equal to DL. So ADL will come here. Now ADL and ADL, now we'll write ADL minus 2 nu ADL is equal to ADL plus LDA. Now here ADL and ADL will be cancelled out. ADL and ADL will be cancelled out, and we can say that 2 nu ADL is equal to LDA minus. Okay. Now, after this, we will put this value here in this expression here, and we will get dr as A rho dl, this A rho dl plus this multiplied by A, right, minus rho LDA. Rho LDA, LDA can be replaced, this LDA can be replaced by this LDA, and here we will be getting plus 2 nu A dl multiplied by rho. We can take A as common, and we can find D, we can write dr is equal to rho dl 1 plus 2 nu, because rho dl we will take from here, rho dl, this will club these two. Right. So we will be getting rho dl 1 plus 2 nu A by A square. So we can write divided by A plus L d rho divided by A. Right. Now, after this, we will divide this dr by R. R is equal to, as we know, R is equal to rho L by A. So entire expression will be divided by rho L by A. This is also rho L by A. Now here rho will be cancelled out, A will be cancelled out, A will be cancelled out, and L will be cancelled out. And this will lead to the expression dr upon R is equal to dl upon L 1 plus 2 nu plus d rho upon rho. Now we have to take dr upon R. So dr upon R is equal to 1 plus 2 nu plus d rho upon rho divided by dl upon L. Sorry, it is capital L. And this is divided by dl upon L. So dr upon R divided by dl upon. Now this dr upon R and dl upon L, it is gauge factor. It is gauge factor. And this, if you neglect this or this remains unchanged, change in specific resistance and change in with the strain, then it is 1 plus 2 nu. So 2 times Poisson ratio. Poisson ratio For metals, it varies between 0.3 to 0.4. Let us say 0.3. So 0.6 for metal, it is going to be 1.6. But we have semiconductors, though they are having the gauge factor as 100 and 150 and 200 as well. Right? So that is why nowadays semiconductors and piezoelectric materials, they are becoming very popular for strain measurement or to work as a strain gauge. Now, after this, we will take up one in numerical. Consider a single strain gauge of resistance 120 ohm. So, resistance of the strain gauge is 120 ohms, right? And mounted on an axial direction on an axial load specimen of steel for steel, E is equal to 200 GPa. This is the resistance of the strain gauge is 120 and E for steel is 120. The percentage change in the length of the rod due to loading is 3%. So, strain is equal to dl upon L is equal to 0.03. This is a percentage change of the rod. And the corresponding change in the resistivity of the strain gauge material is 0.3%. So, change in the resistivity, that is d rho by rho, is equal to 0.003. It is 0.3%. So, d rho by rho is equal to 0.003. Estimate the percentage change in the resistance of a strain gauge and the gauge factor. So, first of all, dr by r. So, dr by r is d rho by rho plus dl by L 1 plus 2 nu. We have already done that. Now, all the values are there. D rho by rho is 0.003 plus dl by L is 0.3 strain 0.03 and 2 nu is 1 plus 0.3 into 2 into 1 plus 2 into 0.3. Poisson ratio is 0.3. It is given. So, with the help of this, we can always find dr upon r, and dr upon r in this case is 0.051. That is, or we can say 0.51 percentage change in the resistance. Now, for gauge factor, we will divide this dr by r by strain, that is dl by L. So, when we divide this dr by r 0.051 to 0.03, we get 1.7. So, gauge factor for this strain gauge is 1.7. Now, the next part is a little interesting. If the strain gauge is connected to a measuring device capable of determining the change in the resistance with an accuracy of 0.02%. So, it is connected to a device which is capable of measuring the strain with an accuracy of plus minus 0.02 ohm. So, accuracy of the measurement is plus minus 0.02 ohms. So, this strain gauge is connected to a device, to a measuring device capable of determining change in resistance with an accuracy of plus minus 0.02 ohm. What is the uncertainty in the stress? So, uncertainty in the stress, because stress is strain multiplied by E, right, or is equal to delta R over R multiplied by E divided by strain gauge. That is strain, because delta R upon R divided by strain is equal to gauge factor. So, here we have used this expression and we have replaced strain by delta R over R divided by Sg. Now, del sigma over del d delta R is equal to E over R Sg. We have differentiated it with respect to delta R. Now, So, uncertainty of measuring stress is equal to plus minus E over R SG, that is multiplied by uncertainty in measurement of R. And this is going to be equal to E is 200 into 10 to power 9 divided by resistance is how much? 120 ohms. 120 multiplied by, if you remember, gauge factor 1.7, and uncertainty in the measurement of resistance is 0.02. So this will be multiplied by 0.02 and we will get 19.6 megapascal of plus minus 19.6 megapascal in the error in the measurement of stress, right? And strain, uncertainty in strain is also required. Error in the measurement of strain is also required. So for finding out the error in the strain is uncertainty in stress divided by E, that's it. So uncertainty in the stress is 19.6 divided by 200 into 10 to power 9 is equal to 98 into 10 to power minus 6 or 9.8 into 10 to power minus 5, right? This is the uncertainty, or it is, we can say 98 into 10 to, or 9.8 into 10 to power minus 5. Okay. Now after this we will continue our discussions on bonded strain gauges. So I will give you some idea about the gauge factors for constant end strain gauge, where wire is constant end, where the in constant end the composition is nickel is 45%, and copper is 55%. It is, the gauge factor is approximately 2.1. So metals and alloys, for metals and alloys, the gauge factor is, I mean, it, if you change the composition, for example, if you take nickel 80% and chromium 20%, nickel chromium alloy, then nickel chromium alloy, the gauge factor is 2.1 to 2.63. If you take single crystal semiconductor, the gauge factor may lie in a range of 100 to 170. The gauge factor in the single crystal may lie in a range of 100 to 170. So you can compare. We are going for the metallic type. In metallic type, it is not exceeding even 3. But here the gauge factor for semiconductor is lying between 100 and 170. There are certain factors which affect the performance of strain gauges. First of all, temperature variation, and second is humidity. There are two main factors which affect the performance of a strain gauge, because when there is a change in temperature, there is a differential movement between substrate and the strain gauge. They may not have same coefficient of expansion or contraction. So this stress, or the force, or I mean the relative motion between these two causes the slip of the strain gauge, and in that case the right kind, the reading will be affected and we will get the erroneous reading. So that is one thing. And in the due to humidity, insulation breaks between ground and the strain gauge. The insulation breaks and it causes corrosion of the wire also sometimes. So due to humidity also, so the strain gauge has to be saved first of all against the humidity, and second, there should not be much temperature variation in the environment. And there are another type of strain gauge which is known as foil type of strain gauge. They are also becoming very, popular nowadays. And regarding the semiconductor strain gauge, they are normally made from silicon crystal. Silicon crystal. And for designing the strain gauge, the in semiconductors, orientation in doping is important, right? So if you do, if you increase the doping, then it affects the resistivity of the strain gauge. Resistivity is reduced, right? So right kind of doping is required. Germanium is also used as a also be used as a strain gauge. And P type of semiconductor have positive gauge factor, and N type of conductor have negative gauge factor. So sometimes negative gauge factor is beneficial, because if there is a variation in temperature, that can be compensated, right? But if we want linearity, then we should go for P type of semiconductor. Definitely, they are made of semiconductors. They are quite fragile, so they have to be handled with care. And they have very high temperature coefficient. Coefficient can go up to 1.15 degrees centigrade. Sorry, 0.15 per degree centigrade. This is the temperature coefficient. So doping is a very important parameter in designing of a strain gauge. If there is a light doping, then gauge factor is high. If we do the high doping, if we increase the doping, in that case gauge factor will reduce. At the same time, temperature dependence of the sensor will also reduce, of the strain gauge is also reduced. So a designer has to strike balance between two, and has to decide right kind of doping, so that we maintain high gauge factor for the strain gauge, and at the same time the temperature dependence is as minimum as possible. So in fact, these type of strain gauges, semiconductor strain gauges, they are inherently non-linear. They are not very linear. They are and if we decrease the doping in the strain gauge, we will get high gauge factor and high non-linearity also. But in order to address non-linearity, nowadays ICs are available which can make the non-linear signals into the linear signals. So this is all about the strain gauges, which are widely used for research and industrial purpose. In the next class, we will start with the piezoelectric transducers.